Okay. Now, we would like to start with calculus. And for doing differentiation of trigonometric functions, we will need a couple of special limits also. So, we need to look at that trigonometric function limits. And before that, I would like to introduce the concept of continuity. Continuity is a first concept which is a preliminary requirement for calculus. So, what is continuity? Obviously, we are going to use a epsilon delta style definition for this, so to make it more rigorous. Continuity intuitively is a continuous function. No? That means, if you say I plot a function on the y-axis, values of the function on the y-axis corresponding to the values of x on the x-axis, I get a point, and I get so many points for the function, and if I can join all those points with a continuous line without lifting my hand from the board or paper, we call it a continuous function. How do you define that? This is intuitive definition. How do you define continuity of a function? First, we define continuity of a function at a point first. And then we say we will define continuity of a function in an interval. For example, you take AB as an interval, can be closed interval or open as the case may be. We can perhaps look at a closed interval, AB, square brackets, A comma B, which means all the points between A and B inclusive of A and B. That is the set of points. And we would like to see whether a function is continuous in this particular interval. Now, obviously, this interval must be within the domain of the function. A function is defined always for only a subset of real numbers, which we call it the domain. And polynomial functions. Now, what is a polynomial function? Which can be expressed as a polynomial of any degree of the variable x. I can write one polynomial function. You want to call it f of x as some a0 plus a1 multiplied by x plus a2 multiplied by x squared plus etc. plus a n or maybe a n minus 1 multiplied by x power n minus 1. No? So, this is a polynomial function. We are writing it from the lowest degree first to the highest degree on the right hand side. Unlike a decimal number, we would have written in the other way around. No? So, the same decimal number has the same representation, x is 10 in that case, but we write that in that other order. Reason is very simple. We would like to write this because we want this n to be able to go as large as we want, including going up to infinity. I can't start with that infinity first. No? I can't say something multiplied by x power infinity plus infinity minus. I can't write it in that order. So that is why we are writing in the wrong, you can call it wrong order if you want, wrong with respect to what we wrote decimal numbers. In fact, decimal numbers themselves are wrong order. It should have been written like this, but then somehow we have got used to writing it the other way around. No? So, doesn't matter. This is known as a polynomial function, and a polynomial function, first thing is its domain is the entire real axis. That means it is defined for each value of x on the real line. Secondly, it is continuous throughout this. So, it is totally continuous in its entire domain. So, we just call it fx is continuous, period. When you say fx is continuous, just plain statement without specifying any interval, which means it is continuous everywhere in the domain where fx is defined, of course. We can't go to places where fx is not defined. We are only looking at parts of the domain, right? So in the entire domain, if it is continuous, we simply say a function is continuous in that domain. Now, we need a technical definition for this continuity. How do we do that? First, we define continuity at a point. Take any point, A, for example. So, how do we say a function is continuous at that point? Right? First thing is, it must be defined at that point. See? That means there must be a value of the function f. If you say this is the function f, that value is fa. Function itself is fx, f of x, where x is varying from all over real values, and a particular value of x I want, so that is a. Therefore, f of a is the value of the function at the point a. So that is the altitude at that point, right? So f of a, first of all, that must be defined. So if it is not defined, there is no question of continuity. For example, if you look at those pathological functions which I discussed, a pathological function which had a hole does not satisfy this, because at that hole, that function is not defined, it's not part of the domain. So it must be in the domain. First thing is, it must be in the domain, and there is a value for it, and it should also be the same as the limit x tends to a of fx. Very simple. So when x approaches a, it can approach from the left side. That is, value is less than a and going up to a and not touching it. No? So that is the limit. Or it can approach it from the right side also. Many times people call it a left side limit and a right side limit. So, but actually we just called it limit because left side limit and right side limit must be the same. Then only we call it a limit. So in this case, that limit also should be the same value as the value of the function at that point. If this condition is satisfied, that means actually there are two conditions. One is function must be defined at that point, has a value, and second is the limit of that function as x approaches that value must be the same as that value. So in that case, we define, this is the definition, saying that function fx is continuous at the point a, one point continuity, it's continuous. Then obviously we can extend the same thing. If you say I got an interval like closed interval a comma b, for example, we are saying function, this is the definition, function fx is continuous in this closed interval if it is continuous at every point in the interval. That means for all x, that is the condition, x belonging to a point on the closed interval a comma b, for any x value in this interval. So we write it like that. No, this is belonging to, this is not epsilon, this is trishula. No? So the trishula belongs to that interval. No? So x is a point in that interval. So we write that. So for all or for any x belonging to that also they have a notation for it, saying for any x belonging to the interval is written with a inverted a. I don't know why they write it so. So this is for any x belonging to this, we satisfy the condition that this limit of x tends to x only. I mean, this is x. Maybe I will say y tends to x. I'll just change the name of the variable. X is after all just a symbol for the value which we are changing in the domain, right? So I've got a y which is changing in the domain. For any x, the y is approaching that x, and that f of y, that is the value at a y, must approach f of x. So this is the definition of continuity in that closed interval. You can have an open interval also, doesn't matter, whatever interval. So this is the definition of continuity. So once you have continuity, which means I have a curve which I can join without lifting my pen, which also means that I can walk on this line. Just imagine a tiny ant trying to walk on this. It can walk on this because it will find everywhere, it finds actually a part of that function as a step, as a road. No? It's like a road here. Imagine it is a road on which an ant is walking. Obviously it can walk across, no? Because there is no hole there. So if there is a hole there, it can't walk across. No? So, or if there is a step there, no? Like a step function, pathological function that you have seen, if there is a step, ant cannot take that step. So obviously it cannot walk across that function. So basically this is like an ant walking on that graph, means continuous in that range. That is one aspect. Now I'll take another example of the function that we had for the modulus function. So how does the modulus function look like? We've seen is a 45-degree line at 0 and a reflection of that on the y-axis. the other side, correct? No? Now this is continuous because it goes past the 0 and goes up, right? Straight up and can walk across. So this is continuous because you can see limit. The left hand limit when it approaches 0 is 0. Right hand limit when it approaches 0 is 0. Value at 0 also is 0. So therefore it is continuous at 0 and continuous elsewhere. So no question of it. So the function f is equal to mod x is continuous in its entire range, or sorry, entire domain. It's just continuous. No questions on it. But we are going to find some problems with such functions. I will show a slightly different picture of that another function, which is basically a mirror reflection of this function on the x-axis as a mirror. No? Just visualize that. What will it look like? It will look like something like this, like a mountain, correct? No? Supposing I have a function like this, actually it is a pathological function. I will show you why. Now, an ant can walk on this mountain, no problem. It can go there and continue downhill like this. But supposing you have a car and you want to drive on that mountain road. It is a road on the mountain, no, which is taking what you call a sharp turn. It's a sharp turn. No? Now try driving on this road. You can't. When you hit that, you can't drive. No? You get stuck there. So you can't drive fast. No? So for driving, what you need on a road is something like this. Correct? No? See the difference between the two. What is the difference? Now, can you notice the difference between the two? See, now I can drive on this. Smoothly, I can drive, right? Whereas this I can't drive because it is not smooth. No? So this is not smooth. It is continuous, but it's not smooth. I mean, what is this smooth? No? Intuitively, we are saying it is not smooth. Other road is smooth. So on a smooth road, I can drive. No? So, see, remember, for driving, when you say you got a car which is driving on a road, car has got a face, no? Front, has got a front, has got a back. So at any point of time, you can see car is facing one direction. No? You can see it is facing one direction. So, now that direction, there is a direction there. No? That direction itself is changing when you are driving, you see. In the case of a smooth graph or a smooth road, the direction is changing slowly. Incrementally, infinitesimally it is changing. So we can drive across that smooth function. Whereas here there is a sudden change of direction. The problem with not smooth is sudden change of direction. That is the intuitive understanding of that. Sudden change of direction. So when you have a sudden change of direction, obviously it cannot drive. You can't suddenly say like this. No, car cannot suddenly change its direction. It can only change it smoothly. No? So that is the definition of that. And one more aspect, if you see the car, what is the direction of the car? Wherever it is on the smooth road, you can see it is always tangential to the curve. It is tangential. Always tangent. You can see that it is always tangential to the curve. Right? So the tangent is tan. Itself has got to be continuous. No? So tan is a derivative. Actually, that is a differential. We are defining that as the differential. Is something like an instantaneous rate of change is called that direction. That direction change, direction itself is instantaneous change, right, of position. And that has been one direction, no, smoothly. So that is a differential. That's how we define a derivative as a tangent of that graph. If you can draw it on the y-axis, the tangent will be the derivative of that. And when that makes a sudden change in the derivative, obviously you can't drive it. So there is no derivative there. So that means at this point, at every other point we can drive. No? So every point it is fine, it is smooth. But at this one particular point on the peak, it is not smooth because there is a sudden change of direction. Because still here, car is facing northeast, you can see that. And beyond this point, it is facing southeast, correct? No? So there is a change of direction from northeast to southeast at one point, no? Sudden change. So sudden change of direction cannot be used for driving. No? So we are saying at that point it is not smooth. So what is the meaning of smooth? Is differentiable. So this is known as differentiability. Just like we had continuity, we have differentiability. Differentiability is the technical definition for smoothness. So a function can be differentiable at a point if it is smooth at that point, if there is no sudden changes of direction basically at that point, and it is differentiable everywhere if it is smooth everywhere. No? Luckily for us, the polynomial function is smooth everywhere, so we can derive it everywhere. No? It is differentiable at every point in its entire domain. So we want to now define that. What is this differentiability and how do we define that smoothness using epsilon tech delta method, right? So what I will do is I will just write, I can write the definition for that now, or we can look at, like I said earlier, we can look at a couple of trigonometric functions and a couple of indeterminate limits, 0 by 0 type of limits, because that will be required when we want to look at smoothness of trigonometric functions. Differentiability of trigonometric functions, we will need that smoothness. So why don't we look at that first? So we start with the diagram first as usual. Sine function. Sine is the fundamental, most fundamental trigonometric function is jiva, right? Sine. So we'll start with the sinus. Let me draw the usual angle and diagram. We need an angle for it. So we draw an angle. Basically, the whole thing originated because of navigation. That is parikramana, the circumnavigation that we do. So I can indicate part of that circle. Actually, what I have shown is a sector. This is a sector of the circle. So I got this angle, we can give a name to it. I can call it theta. Greek letter theta. Theta or theta, whatever you want to call it. And this was the original circumnavigation. And in fact, this is almost like the planetary motion. If like a planet, it has gone around like this because this happens to be attracted towards that point, the sun. Whereas his original intention was to go straight up, right? So that direction would be tangential to the circle, right? I showed you earlier how we defined tangent. So it would have travelled up till here, but it actually travelled like this towards the center, some distance. And the sinus value or the sine value will be the perpendicular. To aid our calculations, we can assume any lengths for these because of Thales' theorem of similar triangles. You will get only the ratios are there. So we can assume that the distance, we'll start giving names to these vertices. I'll just call this O at the center. Then I got the original point A from which it travelled to point B because of the circular movement. But if we didn't have the circular movement, it would have travelled straight up to C in the tangential direction to the circle, that's the tangential direction. And from B we drop the perpendicular to the base, which is D. So now obviously we have defined sin theta as BD opposite side by hypotenuse, OB. Now we can set this OB as 1, not OC, OB as the hypotenuse. So sin theta will simply equal to BD. No problem. Correct. Similarly, tan theta. What is tan theta? Is the movement in the tangential direction, is opposite side by adjacent side. So, we have defined that. Is AC by OA. Correct? AC, opposite side by adjacent side, OA. Now, OA and OB are same because remember, this is a circle, no? The circular movement. So, OA is also 1. OA is 1, OB is also 1. Therefore, this is simply AC. This distance is the tangent, tan, and this distance is the sine. You can see sine is slightly less than tan. And we have an arc in between the two. Correct? No? So now, how do we find out, or what happens? Now I have shown this movement from A to B, so much of angle I have moved, right? So that is the theta. Supposing I keep reducing that angle, what happens to this BCAD? Just imagine, just visualize. I make the angle less, no? What happens? D will come closer to A, C will come closer, right? You understand? All of them will start closing up. So that means DB and AC will start getting closer and closer as you move this C towards A. Correct now? You understand? So the question is, what is the value? So I want to find out what is the value of sine 0? 0 degrees. Suppose finally I just touch it. I am not moved at all, man. So where is the opposite side now? What is the height of the altitude BD? When you start with, it is 0 now. Altitude is 0. Therefore, sine 0 is 0. Correct? In fact, angle theta itself is 0 degrees. I am starting with theta as 0. When theta is 0, sine 0 is sine theta, which is 0. Right? So that is 0. Similarly, tan 0 is how much? Even tangential distance, I have not travelled at all, no? It is still 0. It is also 0 only. Correct? No? So now I got a theta which is 0. I got a sine 0 which is 0. I got a tan 0 which is 0. Correct? No? All are 0 to start with. And they start moving from. Once you start moving, they start getting some infinitesimal values, then finite values, and then keep going up. Right? So then one last here is what is cos theta. If it cos theta is adjacent side by hypotenuse. So adjacent side is OD. Hypotenuse is OB. Correct? OD by OB, which is OD itself, because OB is 1 now, we assume. So OD is cos theta, right? But I am not really interested in OD. I am interested in AD. This. What is this distance? Remember, OA is the same. OA is same as the radius, which is 1 now. OA is 1 and OD is cos theta. Therefore, AD must be 1 minus cos theta. And so, what is the value of 1 minus cos 0? So, if we don't start at all, D is actually at A only, you know, that AD is still 0 only. So, this is also 0 only. So, now I got 4 values, all of them are 0 at 0. Theta is 0 at 0. Then sin 0, sin theta is 0 at 0. Sin theta, tan theta and 1 minus cos theta, all are 0 when theta is 0. Clear now? So now we want to do this indeterminate business and see what is the value of sin theta by theta. One question number 1. And what is the value of 1 minus cos theta by theta? I can't substitute theta equal to 0 in these two cases, because then it will look like 0 by 0, which is indeterminate form. Here again it is indeterminate, because 1 minus cos theta is 0, cos 0 is 1 actually. So 1 minus cos theta is 0 and theta is 0. So it's also 0 by 0, both are 0 by 0. So we cannot substitute value of theta equal to 0. So we can only look at it as limits. I want to look at the limit of this. So what am I interested? I am interested in limit of sin theta by theta as theta tends to 0. Theta won't reach 0. It won't touch 0. But it can approach 0 as closely as you want. Epsilon neighborhood. I want to see sin theta by theta has got a corresponding, actually this is a delta neighborhood. So I can reach any delta neighborhood of 0 I can take. And I want to prove that sin theta by theta will be on the epsilon neighborhood of some real value. I want to know what is that real value. Same way, I want to look at limit theta goes to 0 of 1 minus cos theta by theta. That's the question. In fact, if you remember an earlier example that we had worked out, we had x squared minus 1 and divided by x minus 1. When x equal to 1, this was indeterminate, correct? 0 by 0. We cannot substitute x equal to 1 there, but we are saying x approaches 1. X minus 1 approaches 0, no questions. X squared minus 1 also approaches 0. The only question is, which is faster? Something approaches faster or something approaches slower. In fact, we found x squared minus x minus 1 approaches 0 at twice the speed of x squared minus 1. Therefore, the division resulted in a 2. Limit was 2. We found this limit was 2 because x squared minus 1 approaches 0 faster or slower than x minus 1? Faster. That rate is 2. That's why we found that 2 as the limit. Even though it's 0 by 0, limit is 2. Correct now? Same way, we would like to see does sin theta approach 0 as fast as theta or slower or faster or same speed. Similarly, 1 minus cos theta, does it approach 0 as theta approaches 0, same speed as theta or faster or slower? Same thing for tan theta. So we would like to see tan. I am not really interested. No? How do you find out this? In fact, if you ask Greek mathematicians, how would they have found it? I got a geometry diagram, no? But we just look at the diagram. I'll show you how you can find out what are the indeterminate limits, right? Yeah. If you think like ancient Greek mathematicians, when they have a geometric figure, they can worry about areas and things like that. Just look at the way when theta approaches 0, actually we are moving this line. Just imagine. Just a bit of imagination. So this radial line, we are moving towards 0 like this, right? And when we move like that, what happens to these 3 line segments that I have? I got a CA, which is tangent. I got a BD, which is the sine, and I got an arc. Arc is theta itself. Actually, the arc is a measure of the angle. So all 3 are there, and all of 3 will start coming together and together. No? You understand? Now, how do we find out which comes to 0 first and which comes next and so on? Is to figure out, is to look at areas. So now we look at, how do we find out? Something very simple method, because I can always, in geometry, I can always look at areas visually and decide which one is bigger, which one is smaller. No? So no problem. So that means we are looking at 3 areas here. Area of triangle OBD. That is the sine triangle, no? Which gives you the sine. Then I got area of sector OBA. This is not a triangle, it is a sector. No? It's a part of the circle. Got a big circle here with O as the center. A and B are 2 points on the circle, but I can close the circle if I want, right? So the sector is one piece of that, right? That is sector OBA. And lastly, we have area of triangle OCA. This is the point C. It's a big triangle, correct? Now, what can we say about these 3 areas? I know for sure, whatever their areas are, area of triangle OBD is always less than or equal. I will just put that equal because eventually they become equal. No? So less than or equal to area of the sector OBA, which must be less than or equal to area of triangle OCA. Correct? That I can conclude, because you can see that, you can see clearly by the geometry that the 3 areas that I have. So area of OBD is less than or equal to area of sector OBA, which is less than or equal to area of triangle OCA. This is clear. No problem there in that. Now, what is area of OBD? We will start calculating the areas. Is half base multiplied by height. Correct? So what is that? What is the base? Or if you want, you can start with OCA. What is the OCA area? Is half base multiplied by height, right? So half multiplied by, what is the base? OA is the radius. Radius I have assumed as 1, no? Multiplied by 1, multiplied by height. Height is tan theta. So half tan theta is the area of triangle OCA, correct? What is the area of sector OBA? Sector OBA is the area of the sector subtended by the angle theta. How do I find out? For the entire circle, which has got an angle of 2 pi, what is the area I would get? Pi r square, correct? Pi into 1 square. R is, radius is 1 here. So, entire angle is 2 pi. For the entire angle, I get an area of pi into 1 square. Therefore, for an angle theta, I will get an area of multiple theta. Pi by 2 pi multiplied by theta. So, in fact, you can rewrite that as half theta. This is half tan theta. Half theta. What is the area of triangle OBD? BD is sin theta. Half sin theta multiplied by OD. It is actually 1 minus cos theta. No, it is cos theta. Sin theta and OD is cos theta. So half of sin theta cos theta is the area of this triangle. Half theta is the area of the sector. Half tan theta is the area of the bigger triangle. Right? So I have written one inequality already. Half sin theta cos theta less than half theta less than or equal to half tan theta. So we'll just rewrite that here as a separate statement of the areas. So can I say sin theta cos theta, whatever value of theta, small theta, must be less than or equal to theta, which must be less than or equal to tan theta. Right. I can write that tan theta as sin theta by cos theta if I want. Now our interest is in sin theta by theta, correct? How do you do that? When you have an inequality like this, we know that sin theta is a positive number. For a small value of theta, sin theta is positive. So if I divide by a positive number, the inequality does not change. So divide throughout by sin theta. So I get cos theta less than or equal to theta by sin theta less than or equal to 1 over cos theta. Correct? No problem there so far? Looks fine. Correct. So now our interest was not theta by sin theta, but sin theta by theta. So I want to take the inverse of it. When you make an inverse, what happens to less than or equal to becomes greater than equal to. When you invert, take a multiplicative inverse, changes the inequality. If x greater than y, then 1 by x must be less than y. 1 by x must be less than 1 by y. Correct? Always that is the case. So therefore, we'll rewrite this. 1 over cos theta must be greater than or equal to sin theta by theta, which must be greater than or equal to cos theta. Correct? Beautiful. So now just comparing three areas, I got a very nice inequality of our sin theta. Our interest is not in cos theta. Cos theta, when theta goes to 0, is 1. Everybody knows there is no confusion there. There is no indeterminacy there. Cos theta known value. At 0, cos theta is 1. Cos 0 is 1. No questions on it. Absolutely. Our interest was sin theta by theta only. Now, if what happens when, so let us write, what is the limit of 1 over cos theta as theta goes to 0? Cos theta goes to 1, 1 over cos theta also goes to 1. Must be equal to 1, right? And this limit of cos theta as theta goes to 0 is also 1. No problem there. Only thing is, cos theta will be slightly less than 1. When theta is very small, cos theta is slightly less than 1. And it keeps increasing and reaches 1. Whereas 1 by cos theta is slightly more than 1. And when the theta hits 0, it keeps reducing till it hits 1. Right? So, in fact, 1 by cos theta approaches 1 from the right side, slightly higher, lower, and become 1. And cos theta approaches the same 1 from the left side, lower, 0.9, 0.99, and 1. So that's the limit. So it approaches 1 from the left side. This fellow approaches the 1 from the right side. Both of them are approaching 1 only. Right? That's not the point. He is like our breakfast. No? We have one popular breakfast. What do you want to do? My interest is in eating tomato and cucumber slices. That is my interest. Slices. I've taken a tomato, I've taken a cucumber, nicely cut them into tiny slices. No? I want to eat tomato and cucumber. Yeah? But then when I want to pick it up, you see it is wetty, and pick up one cucumber piece, hand becomes wetty, and if my hand is dirty, the dirt will get into it. It's not nice. No. So what we do is we take 2 slices of bread. We take 1 slice of bread first and put all our slices on top of it, whatever slice that you want. Tomato, cucumber, if you like beef, put beef, ham, as your taste is, matter. And even this, if you try to hold it, you still hold that. I don't want to hold tomato, I don't want to hold a sandwich. So put 1 more bread slice on top. Correct. And what do you call this? Is a sandwich. It's called a sandwich. Correct? Sandwich. So once you have the sandwich, now I got a nice, I'm holding bread only. It's not wet or anything, I can eat that. Now sandwich, if you keep pressing the 2 pieces of bread, what happens to tomato and they are not going anywhere. No, tomato is not going anywhere, cucumber is not going anywhere. It's stuck in between these 2 slices. Correct? Now, eventually, if I totally force it down to 0, where is the tomato? It's got to be in between. No, there is no choice. Same way here, when theta goes to 0, we have 1 over cos theta, which is going to 1 from one side. We have cos theta, which is going to 1 from the other side. And our poor fellow, tomato, sin theta by theta, tomato is stuck in between. Obviously, it has nowhere else to go. So what is the limit of sin theta by theta? 1. Must be 1. There is no choice. It's known as the sandwich squeeze theorem. Actually, this theorem is called a theorem. When you have 2 functions whose limits are same, and one power function which is stuck in between those 2 with inequalities, and in that limit will be the same for the in-between function, because basically it is stuck in the inequalities. So it's known as a sandwich squeeze. Exactly what I did, theorem. Now this, I will take that as implicitly understood. We'll assume it is true. I don't know how, whether the rigorous proof can be given. Sure, it can be given. But then I'm not going to sit down and prove the sandwich squeeze theorem. We'll assume as an axiom, actually. I'm sure this can be proved by one of the 4 axioms for real number system. squeeze theorem also can be proved as a theorem rather than assuming it. But remember, we are pre-Bolzano days. No? Our discussion of calculus is pre-Bolzano. I don't want to talk about Bolzano. It is too high funda for me. So we'll make some assumption, but assumption must be correct first of all, and it must be obvious, intuitively obvious to anybody who looks at it. Anybody who looks at the sandwich squeeze knows that sin theta by theta limit must be 1. I mean, there is no choice. It cannot go this side, it cannot go this side, because you got two fellows who are approaching it, pushing it from both sides, and both of them are reaching 1 from the other side. Therefore, limit sin theta by theta is equal to 1 as theta goes to 0. So that indeterminate form goes to 1. Beautiful result, don't you agree? That's what we want to see. The other one was 1 minus cos theta. 1 minus cos theta didn't appear anywhere here. I will still require that. 1 minus cos theta by theta also we require. That we will prove next. That is a simpler way of proving that, how fast it approaches. Now you see, sin theta approaches 0 as fast as theta approaches 0, same speed. Both of them are approaching at the same speed. That means, for example, I'll give you an example. If theta is 0.0000001, 6 zeros followed by 1. What is the value of sin theta? Will also be 0.0000001, maybe a little extra somewhere in the end. 1.00002 or something. Almost the same. Yeah. Sin theta will almost be the same as theta approaches 0. Nearer and nearer and nearer, it will be as close to theta, because both of them are approaching 0 at the same speed. Same speed. That is why that limit is 1. Clear? Okay, so now we look at like I said, I need one more result. I can now rub this. I don't need that geometry for the other limit that I want to prove. Is 1 minus cos theta. A little bit of algebraic jugglery, I will be able to prove the limit for 1 minus cos theta also. So we'll do that. So what is our objective? We want to find out the limit (1 minus cos theta divided by theta as theta goes to 0. We know that when theta hits 0, denominator becomes 0 and numerator also becomes 0, because cos theta becomes 1, cos 0 is 1. So we have a 0 by 0 format, and it's always very interesting to find out limits which have the indeterminate form. Determinate form, we simply substitute the value. There is no question. What is the limit of theta going to 45 degrees of 1 minus cos theta by theta? Simply substitute theta equal to pi by 4. So 1 minus cos pi by 4 divided by pi by 4. That everybody knows substitution. I can just substitute the value, no problem. Only when you have these indeterminate forms, we get a bit of interest. Now I want to see what is 1 minus cos theta, how fast it goes to 0, and how fast theta goes with respect to how fast theta goes to 0 is the question. If you look at the circle, you should get an idea of that. Remember, we are looking at a point on the circle which is tangential to this, right? And the cos is that base. No? That is, if you take a point high enough, I get a cos. This is cosine. Correct? No? O. From point A, I move to point B and dropped a perpendicular. OD is cos theta. Actually, OD, adjacent side to this angle. No? This angle is theta. When it comes nearer and nearer A, now you can see that the path of the point is very close to the tangent. No? You can see that. Very close. So that means cos theta reaches 1 much earlier than theta reaches 0. You can intuitively think like that. Cos theta approaches 1 much faster than theta approaching 0. Theta is point, let us say theta is 0.00001. Then what is 1 minus cos theta? Is not just 0.00001, it is 0.0000000000001. It almost reached 0. Theta is still far away from 0. But 1 minus cos theta, I have already reached. I mean, almost. There is no question of reach. There is no reaching in limit. I have almost reached. That fellow is still behind me. So 1 minus cos theta approaches 0 much faster than theta. How do we prove that? Very simple algebraic manipulation will do that. What we do is, we say equal to. Now supposing I multiply the numerator and denominator by some positive quantity. What happens to the limit? Nothing changes. No. What happens to the value? They say, I multiply this by 2 and this also by 2. For example, I'll just give you an example. I want to multiply 1 minus cos theta by 2. I will multiply theta also by 2. So obviously the limit will be the same now. 2 and 2 cancel, the limit is the same. But 2 is not the number with which I want to multiply. I want to multiply by an almost 2. Remember, cos theta is almost 1, right? So I will say, instead of 2 by 2, I will multiply by 1 plus cos theta. One plus cos theta is almost 2 actually. Because cos theta is nearly 1, correct? Now the reason we are doing this, very simple. We have the age-old a plus b multiplied by a minus b is equal to a squared minus b squared. Remember, that formula we will never forget in our life. Formula number 1. Formula number 2 we will never forget is Pythagoras theorem. Pythagoras theorem is ab squared plus ac squared is equal to bc squared, whatever in triangles. But in terms of trigonometric functions, what is Pythagoras theorem? Sin squared theta plus cos squared theta is equal to 1. That is the same. Adjacent side squared plus opposite side squared is equal to hypotenuse squared. Obviously, sin squared theta plus cos squared theta is equal to 1. So I would like to get the sin squared, cos squared somewhere, but I only have 1 minus cos theta. I want to get cos squared so that I can apply Pythagoras theorem. So therefore multiply by 1 plus cos theta, because that nicely produces that squared without the intervening. I don't like ax squared plus bx plus c. That is not good. X squared minus a squared is very nice. You understand? I'd like to. So that is the reason we multiplied by 1 plus cos theta by 1 plus cos theta. Both. Not 2 by 2. So what do you get now on numerator? 1 minus cos theta multiplied by 1 plus cos theta. And what is that? 1 minus cos squared theta. Divided by theta multiplied by 1 plus cos theta. I can't do anything about that. We'll leave it as it is. Just a positive number. Just a 2. Nearly a 2, right? So just do that division. And what is 1 minus cos squared theta? Is sin squared theta. Divided by theta multiplied by 1 plus cos theta. Now, just now we have proved sin theta by theta limit as theta goes to 0 is 1, right? Which also means inverted. What is theta by sin theta as theta goes to 0 is also 1, obviously. So now, actually I have got a sin theta by theta only is there. You can see it there, so we will split that. We split that as two functions is equal to limit. Limit is there in each of these expressions. I didn't write it. So limit theta goes to 0 of sin theta by theta is 1 factor. I'll write that separately. One more sin theta is there, we'll leave it there. And we have 1 over 1 plus cos theta. So I have written 3 terms here, correct? Now, what is the limit of sin theta by theta? I can take limit of a product of 3 quantities is product of the limits of 3 quantities. So this is one thing which we are supposed to prove as an exercise. So what is the limit of sin theta by theta? Is 1. So this is known, no questions on it. And what is the limit of 1 by 1 plus cos theta? Is 2. Also is known because cos theta is 1. Now 1 plus cos theta is 2. And what is the limit of sin theta as theta goes to 0? Is 0. Multiplication by 0 is allowed, only division by 0 is not allowed. So therefore, what is the limit is 1 multiplied by 2 multiplied by 0 must be big 0. Correct? 0. That is why, like I said, 1 minus cos theta approaches 0 so faster than theta that the division actually gives you a 0 itself in the limit. That's the limit. Is that clear? So now I think we are ready for differential calculus. Okay, now we start with algebra of calculus, I said we have to define differentiability. We have seen limit of a function, we have seen continuous functions, and that's a requirement. So function has to be continuous in order to be differentiable. That is car drivable, put in quotes if you want from the analogy. And how do we define that? Is very simple. You say I've got a function of x, call it fx. Correct. We are looking at a specific value of x, one point, call it a. I want to define that this function f is differentiable at the point a. When do we say that? No, is the question. Is limit of x tends to a, never becomes a but tends to a, of f of x minus f of a divided by x minus a. Now I written f of a, which means value at a must be defined. It is continuous. So we assume, that means we are assuming that a is some point in an interval, open interval, and the function fx is continuous in the closed interval, that particular interval, closed interval, it is continuous, and a is any point in the open interval other than the end point, any other point in between. A is one of the points, and since it is continuous, it is defined at that point, and limit of f as x tends to a is fa only, no questions on that. But now I am not just looking at that, I am looking at how fast fx approaches fa. Fx becomes fa when x becomes equal to a, no questions on that. X minus a goes to 0, of course, right? X also is approaching a, so I want to find out the rate at which the function f approaches f of a is to divide that. So fx minus fa divided by x minus a is the rate, actually the rate, the speed at which it is going towards that is actually the value of the tangent, if you can visualize that. Tangent of that will be that value at that point is the direction in which the car is facing on a smooth curve, at the same tangent of the direction. No? That will be limit of fx minus fa by x minus a. This must exist. First condition is it must exist, right? Then we call it differentiable at point A, and we denote it as, we call it f prime A. F prime single quotation mark, f prime A. F prime denotes what is known as a derivative. The value of the derivative at the point A is f prime A. Right? And derivative at a point A is limit of x tending to a of x minus fa divided by x minus a. That limit is called it f prime A. That's how we denote it. And if you say I've got an interval, maybe I got a closed interval, let's call it c comma d, in which f is continuous. And I got the corresponding open interval. I am excluding the endpoints, because if you include the endpoints, we have a problem. I can't come from behind, no. So I should be able to come from both directions. So I have to exclude those 2 points for differentiability. There's a reason why people use this for rigor in the mathematics. I got any point A belonging to this open interval c comma d. If it is continuous, if it is differentiable at any point between, we say f is differentiable in this open interval. That is the definition of that. And this obviously this open interval must be a part of the domain of that function f, because that's where it must be defined, right? So it must be defined. And it can be in the entire domain also possible. Like a polynomial function is differentiable in its entire domain. We can prove that. We'll look at some of the derivative values of different functions shortly. We'll see that. That's the algebra that I'm talking about. So, is differentiable in the interval? No, because Once you say I got a variable x now, instead of a particular value which is in the interval, I'll say I got an x itself with a value in that interval. I get a value for the derivative, no? I'll call that f prime of x. Right? So that means I got a new function now, actually. I got a function called f prime, which got different values or different values of x, right? Which is a derivative at each of those points. So that's a derivative function. So for every fx you might have in the interval in which it is differentiable, you will have one derivative function. No? That's called a f prime x. Is another function. Fx is one function. F prime x is another function, right? If fx is the position of an object which is moving through space, f prime x is the velocity with which it is moving through space. No questions. Obviously, since f prime x itself is a function, now we can check now. Is f prime x continuous in that interval? Possible. Is f prime x differentiable in that interval? Possible. We go and differentiate f prime x also. What will you get? F double prime x. So, second order derivative. No? So this is the first order derivative. So I can derive the first order derivative to get a second order derivative. In the case of an object moving through space, this will refer to the acceleration. So we have a speed, then we have the acceleration, then we will have the triple order, which is the jerk. Then you can have, I don't want to write 4 chords, 5 chords, 6 chords. It almost looks like numeral literals. No? Sorry. Look like the Roman literals. You don't want to do that. Then what we do is we write that number on top in brackets. So f4 of x will be, this is jerk, this is snap, then f5 of x will be rattle, and f6 of x will be pop. This is pop. Pop noise. Pop noise you hear is the sixth order derivative of position of the object. No? Therefore, by this notation, one advantage is I can look at f of n of x is a nth order derivative of function x. I derive it or differentiate it n times. No? That is f n x. So, that polynomial is, you can say I got a polynomial is k differentiable. Now put a number for it. We say a function f is k dash differential if you can differentiate it k times up to kth order. And a polynomial function is infinitely differentiable. You can differentiate it any number of times, it is valid. No? So it is infinitely differentiable. Whereas you can have a function is only k differential. Beyond that, I can't differentiate it. That is, I can't find derivatives for it. It is not differentiable. The kth differential is not differentiable, then that function is only k differential. Correct? One notation that people use is a popular notation. We'll need this notation when we want to do differentiation of a function infinite number of times. Just imagine the complexity of things involved. We are taking a limit at each time, and again we take a limit, we keep doing that. We get ultimately we get what are called Taylor series. Taylor series is infinite differentiation, infinite degree differentiation of an infinite degree polynomial. Okay. Now only question that I have in my mind is how did Madhava in the 15th century visualize that even before Newton and Leibniz invented calculus, infinite series, which is based on these differentials actually. God only knows the answer to that question. Anyway, that is fine. So now what we want to do next is to find, forget about f prime, f double prime, we'll start with some simple, we'll look at some simple functions. We already seen the continuity, and we start differentiating those to find the derivatives, right? Let us start looking at that. And the simplest function that you can think of is a constant, correct? And what is the slope of that constant is always 0, no? Tangent Tan 0 is 0 and is always parallel to the x-axis. So you can see differential is a tangent function at that point. So if you want the graphic notation, you can have it. Without graphics also you can work. Supposing I got a value c, positive value, and the function takes the same value throughout both sides of x-axis. And that function is f is equal to c. Just c itself is a function. F equal to c is a function. And what is that limit? You can write that limit if you want. F of x minus not f of x. X itself is the point where I want to find the limit. So we need another variable, so I will call it f of y. F of y minus f of x divided by y minus x. As limit x tends to y, or y tends to x. And if this is confusing, I'll write back to the x and a notation, the same. I have substituted x instead of a, therefore I have written y instead of x. That's the only difference. So I want to find out for fx at the point x, this is the x-axis. And any value on the x-axis, I'm just calling it x also. At this point, I want to find the derivative of that function. So that means I want to approach this x from either side. So I need another variable for it, so I just called it y. And that y approaches x. What happens to the value of fy as it approaches fx? Is the question, the rate. Whether it is as fast as y minus x or slower than y minus x, or same speed as y minus x, just like we answered for sin theta by theta. We want to look at that. In this case, we substituted fy is c, fx is c, everything is c, right? No question on that. So this will be c minus c divided by y minus x. Now this is not indeterminate. C minus c is 0, all right. But y minus x, we never assume it to be 0 because y only tends to x. We never touch the x now, that's the reason. So there's always some non-zero value is there. So 0 by non-zero value is always 0. So slope is 0. In fact, slope of the line is 0. No? Tangent line is 0. That is for a constant. Now we take other example. Simple example will be this 45-degree line. 45-degree line, tangent is 1 actually. Tan pi by 4 is 1. No? So we will derive that. No? And that function is f is equal to x. Correct? So we want to find the limit. What is the limit? What is the derivation? Limit as a variable y tends to x of f of y minus f of x divided by y minus x equal to limit y tends to x f is x, yeah. Anytime whatever value of x you have, the same value y for f. So fy will be y, fx will be x, y minus x divided by y minus x. And the x definitely is not equal to y. We don't touch y doesn't touch x, so it's non-zero. I got a non-zero value divided by non-zero value, both are equal, therefore this must be equal to 1. It's actually tan pi by 4. This angle is pi by 4, tan pi by 4 is 1. The slope of that. Slope of the curve at the point is the derivative actually. And in fact, when you are driving a car on that curve, you can see car is facing always in the tangential direction. So I need a smoothness there. This tangential direction has to always change over smoothly, not suddenly. So that becomes, it's not differentiable if there is a sudden directional change for the car or the slope or the tangent, whatever you want to call it, and that is a derivative, right? So now there is another way, that is I can write if f equal to x, what is f prime of x is 1, right? We can write that. People write that in another format also. I got a function fx, and when I derive it, we denote that as d by dx of fx is also another way of writing the same thing. We are differentiating with respect to x, dfx by dx. This is not the same as the infinitesimal calculus which Newton did. What Newton was saying that x, we make a small change in x, infinitesimal change in x, call it delta x. There is no question of limit here. And it's not a tiny value alone, it is very, very small. No? The very tiny value of x is called delta x. And when x changes by the delta x, what happens to f? Will change by a delta f. Correct? So delta f by delta x. In fact, you can see here, that is what I have written here. Y minus x is delta x. The small change in x is y minus x. It's actually delta y in this. Anyway, it doesn't matter. And fy minus fx is the small change in, corresponding small change in f. So we divide the corresponding small change in f divided by change in x. Very small, and that ratio is the derivative. Actually, it's not the same because we only look at limits as the modern definition, not as infinitesimals like Newton did, but value would get the same. No? As long as you assume, I mean, if you want to write, you can say limit delta x goes to 0. If you write it, it becomes the same as df by dx. This would be the same as df by dx. So now x, we differentiated a constant function, we differentiated a y equal to x or f equal to x. Now we go to the next level of functions. Remember, we want to start looking at polynomials. So the first thing is to look at a quadratic function, degree 2. And the simplest of those is x squared. Supposing I got an f of x, which is x squared. This is the function. If you want to plot it, you can plot it. When x equal to 0 is 0, and either side it is positive, so it goes like this. That's the graph. It's a smooth graph. You can see, you can drive a car on that. No? If x equal to x squared. Now, how do you find that? As usual, at any point x, so we take a variable y which approaches x, and the value of fy will be y squared minus value at x, x squared, divided by y minus x. Correct? Now, we are back to the same old a squared minus b squared. So, no problem. We can write that as y minus x multiplied by y plus x divided by y minus x. As long as y doesn't actually touch x, y minus x is just a tiny quantity. No? It's not 0. And I got the same y minus x, so I can cancel those two. And y plus x in the limit, of course, is actually x plus y, y is almost equal to x. So, therefore, in the limit, y will be actually equal to x. No? So, the limit will be 2x. So, df by dx is 2x when it is x squared. Now we go to next function, fx is equal to not x cubed. We don't go, x and x square is done, next we go to x power n. Any finite number, x power 10, x power 20. It can't be infinity, of course. Infinity is not a number. X power 1000 also, doesn't matter. If x equal to x power n, what is the limit? The question. Therefore, how do we find that? Is now I can use that delta format of saying I got some x, yeah, that value of that function at an x coordinate. Actually, I want to approach x from either side, from a close point. Now that distance we will call it delta x. It's not actually an infinitesimal because you're going to make delta x go to 0. So that is delta x. Correspondingly, this function has changed a value, correct? And that will be the delta f, the change value. And the limit of delta f by delta x as delta x goes to 0 is that df by dx. This is the same. Actually, practically the same definition. Instead of writing x minus a as x approaches a, I have written delta x as x approaches x only. That's the only difference. It's the same. X minus a I have written as delta x, and f of y minus f of x I have written as delta f. I have just substituted with the delta because easier to do the algebra here. That's the only reason. So therefore, now we'll write that same limit. So how do you differentiate this fx equal to x power n? Is a limit of delta x goes to 0 with the same as x goes to a at any point, delta x goes 0 at x itself. Because it is differentiable in the entire domain, I can use x itself as the point at which I want to differentiate, instead of using one point called a, and then b, and then c, and generalize and say for any x the value is the same. No? So instead of that, we are doing that. That's the only difference. So delta x goes to 0 of, so what is the value of fx? What is delta f? Delta f is f of x plus delta x minus f of x. So how much fx changed? Fx value was fx when x was x. When x had a value x, the function had a value fx. So now I increase x by delta x. So what is that in this case? Is limit of x plus delta x to the power of n minus x to the power of n divided by delta x as delta x goes to 0. If you can evaluate this limit, that will be the derivative of x power n at any point x. Now we can expand this. This is our popular binomial theorem, a plus b to the power of n, right? We have seen that before. Let's write that. So limit delta x goes to 0 of, what is a plus b to the power of n? Is x power n plus nc1 x to the power of n minus 1 delta x plus nc2 x power n minus 2 delta x squared plus etc. Right? Let's not even bother writing the other terms. Next time we'll have delta x cubed, then delta x power 4, and so on, all the way till the end, which will have delta x to the power of n, right? Let's not bother. Minus, of course, I have minus x power n is there. So minus x power n, original value of the function, whole thing divided by delta x equals, now, this x power n cancels off with this x power n, correct? And when I do that, I can take delta x as a common. Everything else has got a delta x. Remember, there is a delta x to the power of n here and delta x here. Every other term has got a delta power of delta x except these two terms which have got cancelled. Therefore, I can take out the delta x as a common factor, which get divided by delta x. Remember, delta x is never going to be actually 0. So you can always divide both numerator and denominator by delta x. No, it's a small number. Therefore, we are going to have limit delta x goes to 0 of, so what is the first term there? You have removed delta x, correct? Correct. Did I make a mistake? is NC1 x to the power of n minus 1 plus NC1 x power n minus 1 is there, delta x divided by delta x is gone, plus NC2 x power n minus 2 multiplied by 1 delta x, of course, because out of the 2 delta x's that we had, one got cancelled, plus etc. Each of the succeeding terms has got a delta x and a power of delta x squared, delta x cubed, and so on, right? And the only term which doesn't have delta x is the first term. So when you say what is the limit delta x tending to 0 of NC1 x to the power of n, this has nothing to do with delta x. I've got only x here. NC1 is a fixed number. I got a variable called x. I'm raising it to the power n minus 1. There is no delta here anywhere, right? There is no delta x. So I can just take it out of the limit. It's not there. Right? Equal to NC1. NC1 is n. What is NC1? N. Binomial coefficient multiplied by x to the power of n minus 1. Correct now? That is the first term. That doesn't depend on delta x. Whatever happens to delta x, this remains the same. Now every other term as delta x approaches 0 will become 0 because they get multiplied by 0. Each of the other factors are multiplied by delta x or powers of delta x. They go to 0. So the limit is nx to the power of n minus 1. So what is the derivative of f equal to x power n is nx to the power of n minus 1. That is the derivative.